Hi everyone, my name is Havan Fu from India. Today I would like to present my paper accepted at date 2020. The title of the paper is Towards Generic and Scalable Work-Length Optimization. The work has been done under my two supervisors, Tomofumi Yuki and Olivier Sontier. Energy consumption is one of the major issues in computing today, shared by all domains in computer science for embedded system design. There are many applications in big data, IoT network, artificial intelligence, high-performance computing, where the energy consumption is one of the most important metrics for designing the system. Approximate computing is a promising solution to offload the energy consumption demand. In computing today, the main idea of approximate computing techniques is to reduce the precision to gain in performance and cost, which can be circuit area for chip design and energy consumption. In fact, there are many applications don't need the exact computation because of the perceptual limitation of human sense. For example, an image can be displayed in different qualities depending on the purpose of the user. So all of these make the approximate computing techniques to be more promising in solving energy efficiency problems in computing today. So for fixed point arithmetics, it is one of the candidates for approximate computing to trade off between the accuracy and cost. It is commonly used in embedded systems for FPGA and ASICs because it is energy efficient solution and preferable for many applications in the domain of embedded system design. Fixed point representation is generally a way to encode a real number. It has two parts, the integer work length part and fractional work length part. The integer work length is responsible for covering the dynamic range of the represented number, whereas the fractional work length is used for fine-tuning the precision of the number with a quantization step equal to the weight of least significant bit. Work length optimization is process of determining the integer work length and fractional work length for every variables in the application, so that the cost in area or energy is minimized, whereas the precision loss is acceptable. Some studies show the uniform work length optimization, where the work lengths of variables are the same. However, the current approach focuses on multiple work length optimization, where the work lengths of variables can be different to obtain more energy saving from the accuracy and cost trade-off. In this study, we show the fractional work length optimization, where we need to find the good work length configurations of the fractional part so that the output quality satisfies the quality constraints with the minimum cost. The fractional work length optimization is an NP-hard problem. It has a complexity increasing exponentially when we consider all the combination. From now on, I use the term work length optimization as a meaning of fractional work length optimization in my talk. From previous slide, we can see that the fractional work length optimization is an NP-hard problem. So to try every combination and choose the best one as brute force is impossible for application containing many variables. So the heuristic is commonly used to solve the work length optimization through the iterative process. So most of the approaches use the variance of the gradient descent algorithms to solve the problem in polynomial time, such as min plus 1 bit, max minus 1 bit, tabu search. However, it still faces the scalability problem when the application containing a lot of work length for optimization. The heuristic is gradient-based algorithm, so it evaluates the neighboring solution to find the best gradient each iteration. When the number of variables increase, the number of solutions for evaluation increase quickly. Besides, fixed point simulation is 1 or 2 order of magnitude slower than the floating point simulation, so all of these make the exploration process can be very long and face a scalability problem. We propose an approach to solve the scalability problem in work length optimization. The key idea of our approach includes: first, we decompose the application containing every variable to kernels to reduce the complexity of the original problem. Then we construct the model to evaluate the impact of each kernel to cost and accuracy trade-off of the original problem. From that, we solve the resource budgeting problem to find the appropriate resource to each kernel. The resource is accuracy, which is a trade-off with the cost in kernel output. Finally, the solution of the original problem is the combination of the solution of the kernels. It is worth noting that the approach is generic, trying to model constructed empirically. So the rest of the presentation is outlined as four main parts. The first part, I'm going to talk about the concept of null budgeting, which is the techniques we use to decompose the application into kernels. Second, I'm talking about the proposed approach and explains how we can construct the model. Then I give you some results through the evaluation and discussion section. Finally, I summarize the talk and give the future work. First of all, I'm talking about the concept of the null budget. So for the concept of null budget, given an application with three kernels, which may be the DSP algorithm or the computation task. In the beginning, full precision expression is due for all kernels of the application, which is expressed by light blue. Then, to identify the work length for all variables, work length optimization is applied for three kernels simultaneously with the constraint lambda objective at the output. We call this way is the global work length optimization or the global search. Instead, to avoid the high complexity of global search, work length optimization is applied to each kernel independently with the constraint lambda k1, lambda k2, and lambda k3, respectively. We call this way a local search. After this process, we can obtain the local solution that express the work lengths of variables in each kernel. Then we can merge them together to obtain the final solution. So given lambda 1, lambda 2, and lambda 3 as the constraints of each kernel, so that the merged solution satisfies the requirement accuracy constraints. Lambda objective. So we call the lambda 1, lambda 2, and lambda 3 as the null budgets. So now the question is how to find the null budgets lambda 1, lambda 2, and lambda 3 so that the final solution satisfies the accuracy requirement at the application level, lambda objective, with the minimized cost. So for the existing approaches, there are a few approaches studying on how to find a good allocation of null budgets. Parasha in 2013 used an analytical model to capture the interaction among the kernel through cost and accuracy. However, because of using analytical model heavily, the approach is limited at the linear system and not parametric. Novo in 2013 used the idea of null budgeting, but this study does not allocate the null budgets. The main idea is that local search is first performed for each kernel to find the Pareto frontier of accuracy and cost. Then the combination of the local search is explored to find the final solution. The main limitation of this work is the final solution is restricted at the design found by local search for each kernel. If the local search is too close, it may miss the important designs. If it is too fast, it can face the scalability problem, making the execution time is very long. Now I'm talking about our approach. Given an application which can be decomposed into n kernels, the objective is to find the appropriate null budgets lambda 1 to lambda n. So when we cut the application into kernels, The main problem is the inter-kernel interaction is missing among the kernels. So the idea here is to recover the connection among the kernels and find how budgeting the noise to each kernel affects to the total cost and accuracy of the application. So to do that, we construct the cost function and accuracy function with the association to the noise budget in step 1 and step 2. Then obtain the noise budget through solving a constraint optimization problem in step 3. So in this slide, I give you the way we construct the cost function. So the first step is to construct the cost functions to find the relation between the noise budget and cost. So for each kernel, some local search are performed to have some initial design used for constructing the empirical model. The figure here shows the designs with cross marker presenting the trade-off between the cost and accuracy found by the local search. A Pareto frontier is chosen as a cost function because it represents for the minimum cost given a noise budget, which is represented by the blue line here. We apply the same process to other kernels. Because the cost function of one kernel is independent to each other, so the total cost is simply the sum of individual ones. So in this slide, I show you how the empirical data is collected from the local search. As I mentioned before, we perform some instances of local search to have initial design to construct the cost function. The figure shows the immediate designs found by different local search for kernel demosaics, which I represent in the result section. Here we use the structural similarities SSIM as the accuracy matrix and cost is the energy consumption, which is normalized. In practice, we perform 3 instances of local search. One is to close to the objective targets of application, lambda objective, one near to the highest possible accuracy, and one at the middle point. The design points found by each local search with a target is colored differently. For example, here the blue is a design for the local search with target 0.91, orange for 0.95, and green for 0.99. If we just consider only single local search, we can see 2 type markers, smaller and lighter ones for non-optimal solution, whereas the bigger and darker ones for Pareto optimal designs. The question now is, why do we need multiple instances of local search? The answer is simply to obtain a better Pareto frontier by combining all the design of multiple local search. The local search will explore the design near to the target in detail, finding much better the design for the region of interest. By combining the design for multiple local search, we can obtain a better Pareto frontier in a wider scope, as the dashed red line in the figure. So, to construct the accuracy function, the objective is to express the interkernel interaction through the noise budget. To recover the missing interaction between the kernels in terms of accuracy impact, we select the subset of the data points in the cost function each kernel. Then we do the combination of all the data to obtain the pair data, where one part of the data represents for the different values of the noise budget and another is to the accuracies of the application output. The data is due for the polynomial regression to obtain the accuracy function with the association to the noise budget. After having the cost function and accuracy function of the noise budget, we can construct the constraint optimization problem, which can be solved by some common solver. So in this slide, I show you an example of accuracy function, which is constructed for 2 kernel case using 4-degree polynomial fitting. The rest point here is a pair of the data showing the coordinates of the accuracy each kernel, unsharp and NNF, which are the name of the kernel, and the corresponding accuracies of the application output in the vertical. Using a polynomial model, we can construct the smooth accuracy function, which expresses the relation between the null batches and global accuracy of application. Next, I would like to give you the evaluation and discussion about the approach. For the application for evaluation, we evaluate our approach in the context of scalability issue for work-length optimization. We choose in-Mexico processor application for the experiment. Basically, it is in-Mexico pipelines which convert the raw image to the observable image. It can be displayed on normal screen. It has pipeline of sub-kernels, for example, denoising, linearization, demosaicing, color space conversion, and so on. We choose 4 kernels for the experiment colored by orange here, which are denoising, demosaicing, grammar correction, and unsharp. It is worth noting that ISP is a complex application, which is usually fabricated as a chipset for modern camera. In our application, it has 725 computational operations per pixel, or around 6.4 giga operation for 4K image. I would say here that the application is complex enough for the scalability study. To construct the context of scalability issue, we create different scenarios where the number of variables increasing through them. In detail, we have 3 scenarios. The first one, we just consider 2 kernels for work-length optimization as NNM and unsharp, which has 36 variables. Then we add 1 more kernel to the second scenarios and 2 more kernels for the third scenarios. We compare our approach with the global search for quality metric, structural similarities, or SSIM, which is commonly used for image processing. We apply for 2 targets, 0.9 and 0.99. 0.9 usually used for video processing, and 0.99 usually used for image processing. In this slide, I compare the execution time in minutes between global search or global work-length optimization with our approach through different scenarios in order of increasing complexity. You can see for each scenarios, there are 2 column bars here. On the left is the total time of the global search, which has only the exploration process to find the solution. The right is the total time by our approach, which contains model construction time for null-batch string optimization and the exploration time for local search given the null-batches. With 2 kernels, the execution time by our approach is worse than the global search because we need the time for model construction. In the second and third cases, when the number of variables increase, the exploration time of global search quickly increase, whereas the exploration time in our approach increase significantly. It actually benefits from decomposing the problem into sub-problems, even though we still need the time for model construction, but the total time in general is shorter than the global search. The same behavior is also obtained by another accuracy target at 0.99. You can see here the trending through 3 scenarios stay similar. So our approach scales better than global work-length optimization. So in this slide, I show you the comparison in 6 experiments in terms of energy consumption of the final solution found by global search, colored by cyan, and our approach, colored by orange. In general, our approach can find a solution that have the better energy saving compared to the global search. You can see here the energies of solution found by our approach is a bit smaller than one found by global search. And the difference is clear for more complex scenarios. which means that the global search is more likely to be stuck at the suboptimal solution when the problem becomes more complex. In this slide, I provide you some other results. We experimented with FIR and IIR filters with 2 kernels and 3 kernels respectively. The number of variables are 15 for FIR and 31 for IIR. We use PSNR in decibel at the accuracy metric at 50 dB and 60 dB to compare the solution found by global search and our approach. This is a comparison in terms of execution time and energy consumption of the final solution. On the left, you can see the comparison in time. The figure also indicates that our approach scales better than global search when the complexity of the problem increases. The right-hand side is a comparison for the energy consumption of the final solution found by global search and our approach. It indicates the energy cost by our approach slightly worse than global search. So the reason is that FIR and IIR are relatively small applications with a few suboptimal solutions compared to ISP. With a loss of collection among the kernels, global search can find a good solution and avoid the local minima. However, the important is that our approach scales much better than global search in terms of time for obtaining the solution, indicating that our approach is more efficient than the global search. Finally, I would like to give you the conclusion of the talk. In this study, we saw that our approach solves the scalability problem in pipeline data flow applications. In our approach, we constructed the model to express the interaction of the noise batches with the cost and accuracy of application by empirical simulation. Then find the appropriate noise batches through solving a constraint optimization problem, which minimizes the cost for quality target. The proposed approach stays generic thanks to simulation. We evaluated our approach in context of scalability problem and clearly solved that our approach scales better than global search. For the future work, we plan to expand the technique to other complex structures with the recurrence, combined, and separated architectures. We also study the techniques in context where 2 or more accuracy metrics involved, which increase the flexibility of work-length optimization algorithm and bigger application. For the information in detail about the framework we use for the work-length optimization algorithm, you can find it on the link below. It is a project built from G-Code framework, an open source compiler infrastructure developed in kernel. This is some of the reference during the paper. And thank you very much for your attention.